Now, this talk is going to be about a Carnapian framework for reasoning about arbitrary natural numbers. Spoiler alert, a Carnapian framework stands for quantified as 5, where quantifiers range over individual concepts. I'm going to say more about that in what follows. The talk is based on a joint work with Leon Horsten. It was carried out during my visiting professorship, a small visit at the University of Bristol, quite a long time ago. Now Leon is no longer in Bristol, he's in Constance, but he's still interested in the topic, and I think that there are still quite a lot of interesting open questions related to this framework, as well as other frameworks for reasoning about arbitrary natural numbers. So I believe that the topic is still relevant, and I'm going to say more about that at the very end of the talk. So let me start. I'm going to start with some informal motivation, a very short one. So I'm not trying to convince you that this is worth doing, but at least try to hint at why this may be interesting in the first place. Some concepts, well, I'm going to just read that with some additional comments. Some concepts that have been once used in a free-swimming manner have been distrusted at later stages. And the most prominent example is, of course, the concept of infinitesimal, rescued by Abraham Robinson's non-standard analysis and Edward Nelson's axiomatic non-standard analysis called internal set theory. And there have been a lot of other axiomatic approaches after that. And another example, probably less known, is the concept of arbitrary object, whatever that means. So following Gottlob Frege, let X be an arbitrary number, then blah, blah, is viewed as having the same meaning as for each natural number n, blah, blah holds, right? So Frege didn't trust variable objects, and the same can be said about many subsequent philosophers and mathematicians. Still, it seems that it would be of interest to have a formal theory that takes seriously the idea that arbitrary objects are indeed objects, not ghosts, which need to be eliminated using the standard quantification theory, and these can be quantified over, actually. Just like with infinitesimals, we want to treat them as actual objects rather than view them via the epsilon delta definition, right? I will not be concerned so much with the ontological status of arbitrary objects. Neither I will discuss metamathematics of arbitrary objects, because Leon has done a lot of that, and he has written the whole book on that. And I'm going to cite that book at the very end of the talk. So I'm going to be more on the logical side of the things. And I believe that the framework actually suggested by Sol Kripke for dealing with the issues is in fact so beautiful and nice that it's worth investigating in its own right. So it's like, if something is natural enough, it has to have some applications, right? I mean, so I'm going to be more on that formal side of the things. Still, let me say a little bit more about arbitrary objects and about philosophical logicians who have been interested in the topic. So there is the following view. This is from Kit Fine's paper, or maybe a book from 1983. The following view: in addition to individual objects, there are arbitrary objects, whatever these are. In addition to individual numbers, there are arbitrary numbers. And in addition to individual men, there are arbitrary men. And with each arbitrary object is associated an appropriate range of individual objects, concrete objects, its values. With each arbitrary number comes the range of individual numbers, and with each arbitrary man, the range of individual men. And an arbitrary object has those properties that are common to the individual objects in its range. So for instance, an arbitrary object, an arbitrary number, sorry, I'm somewhere here now, is odd or even because, well, just any concrete natural number is odd or even. And an arbitrary man is mortal, right? Because each individual man is mortal. On the other hand, and here's a catch, right? An arbitrary number fails to be prime. Well, and an arbitrary man fails to be a philosopher just because some individual number is not prime and some individual man is not a philosopher. So you can immediately see some problem here. So let me elaborate on that a little bit. Clearly, many people find reasoning directly about arbitrary objects problematic. For consider the following example, which is also from Fine's paper. Let alpha be an arbitrary natural number, whatever it is, right? Then it is odd or even, as Fine suggests, right? Since each individual number is odd or even. But evidently, alpha is not odd because some individual numbers are not odd, and similarly, it is not even. So somehow, this number alpha is odd or even, yet it is not odd and not even. And the question is, can we avoid a contradiction by providing a suitable formal framework? Now, let us think of alpha is something like alpha has a certain property, as it is true that alpha, well, is something. Alpha has that property. Then one can try to employ supervaluational semantics, right? Which is not compositional, to handle the example above. Or you can try to employ possible world semantics. And we're going to see in a minute how it can be done, or at least how one can try to do that in order to do at least with some of the examples. So roughly, one of the ways out have been suggested by Kripke. It was Kripke who suggested in his short note that reasoning about arbitrary objects in general and arbitrary natural numbers in particular can be represented by means of Carnapian model logic with quantifiers of individual concepts. And let me recall that individual concepts are functions from possible worlds to elements of a given domain. So perhaps you have one and the same domain in all the worlds, but an individual concept, it says that this object, it has a different meaning. It corresponds to a different object depending on the world. So in one world, this is 1. This is the number 1. And in another world, it may be the number 5 or something like that. So it's a kind of spread, right? It's a function from worlds to elements of a given fixed domain. And these things are called individual concepts. And following Kripke's suggestion, we can try to develop a formal framework. This is what we do with Leon for dealing with arbitrary natural numbers. Well, or maybe with some other objects, but I'm going to focus on natural numbers. And still, one should notice that a distinctive feature of our presentation will be that we supplement the original model language of quantified S5 with where quantifiers range of individual concepts rather than elements of a given domain directly, with a special intentional predicate of being specific. So we will be able to say in our language that some arbitrary object is not in fact arbitrary, but specific. It's concrete. It has the same meaning in all worlds. It's constant. It's a constant individual concept, which roughly correspond to an ordinary natural number. It should be remarked, however, that Keith Fine's own theory that can be found in his book, Arbitrary Objects, is in fact drastically different. So he uses a different thing. And in particular, he doesn't employ model operators, but he uses expressions reminiscent of Scaling functions. I think that his approach is actually less likely, but he has a number of interesting examples, motivating examples for his approach anyway. And he has a number of interesting papers related to arbitrary objects. So for instance, he claims that using his framework, you can try to reconstruct some of the informal reasoning behind Cantorian naive set theory. And it may be interesting to try to do the same within other frameworks. But this is just a side note. Now, let me go formally. This is what I like to do usually, right? So we're going to work in a language that I will call L. Just this is the language we're going to deal with. So our formal language includes all symbols of the signature of piano arithmetic, because we want to reason about natural numbers, or take any signature that is like be interpretable with piano arithmetic. And together with the following, we have a countable set of variables. Intuitively, these will range over arbitrary objects, that is functions from worlds to the standard natural numbers. Of course, in the meta language, we will denote these by x, y, z, and so on, like usual. We also have the classical connective symbols. Here I only mention negation and disjunction, but all the others are expressible using these two. We also have the usual quantifier symbols. So here I only mention the existential quantifier, and I treat the universal quantifier as a shorthand, but this is not important, of course. And we have also the model operator. Here I choose diamond, you know, like Heinrich Wansing says, right? Diamonds are philosophers' best friends. So I'm going to use diamond, but you may also use box, of course. Read as it is possible that. And what is important now is that we also have an extra unary predicate symbol, SP, read as is specific. It is somewhat similar to the predicate symbol ST, like being standard in Nelson's internal set theory that formalizes non-standard analysis. So it's something similar. It's like standard, but we call that specific or concrete. So this is like an additional predicate, a very special one. Now then the formulas, the L formulas, are built up in the usual manner. Yeah, you have a grammar, and right. So you have equality between terms, something is specific, negation, disjunction, exists x phi, and it is possible that phi. And all the conjunctions, implications, and universal sentences and boxes are treated as abbreviations, or you can directly include them in the language. It's not important. So it's just the usual the language of quantified model logic with an additional predicate SP, and keep in mind that we're going to interpret the variables as ranging over individual concepts rather than elements of the domain at a given world. Yeah, x, y, z are intended to range over arbitrary natural numbers. Well, note that x equals y will not define the identity of x and y, but only their coincidence at a given world, which is something that you would expect, right? So it will be interpreted locally. But if you want to have the real identity back, it's very easy to do that because it is expressible by this formula. You simply say that x and y, they coincide through all the worlds. And this is S5. So we have the universal accessibility relation, or if you like, no accessibility relation at all. I mean, all worlds are accessible from each other. So it just says that x equals y at each world, right? And of course, the first order sigma formulas, the first order arithmetical formulas, are a subset of the L formulas in this definition, and these will be occasionally called purely arithmetical, right? So purely arithmetical are just the first order formulas of in the language of piano arithmetic. Now I'm going to slow down a little bit because we're moving to the semantics. Now, let us fix some non-empty set W, this capital W. It stands for a potential set of worlds. I'm going to write this like purely W. I mean, this beautiful W. It stands for the collection of all functions from W to the standard natural numbers. So it's just the collection of all individual concepts over how am I to call that? Probably it's like blackboard bold n, right? The natural numbers, BBN, right? So these are all the individual concepts over BBN. Now, the elements of W will play the role of worlds, of course, as usual, and the elements of this beautiful W, they will play the role of arbitrary natural numbers. So arbitrary natural numbers is just a synonym within this framework for individual concepts over n. Now, and then you define the semantics in the usual way. I believe that most of you, I mean, know this stuff very well, but I'm still going to go through the formal details. Now, evaluation in this beautiful W is just a function from the variables to individual concepts, right? To arbitrary natural numbers, that is. And of course, it can be extended to all the terms in the usual way. But since we deal with individual concepts, it has to give individual concepts to terms, right? Not natural numbers, right? So, for instance, what is zero? Zero is just the zero function. It maps each world to zero. What is S of t? Well, suppose that we already know what is t, right? So gamma of t is some individual concept. And now if, oh, so I did that wrong. Okay, so this is some individual concept. Then you apply it to some world, you get a real natural number. And then you apply the successor function to it, so that you get +1. So roughly, you take the individual the function that corresponds to S of t, and you add +1, right? For each world, at each world. And similarly for addition and multiplication, they're defined component-wise. So you already know what is gamma of t1. This is some function from worlds to natural numbers. You already know what is gamma of t2. This is again some function from worlds to natural numbers. And for a given world, you compute this function, you compute that function, you add them so that you get a new natural numbers. So it's just defined component-wise. So roughly, this is just the sum of two sequences indexed by worlds, and this is the product of two sequences indexed by worlds again. Right. And also, I'll use an additional notation for each natural number, not arbitrary, right? For each concrete natural number, I will denote the corresponding constant function by bold n. So bold n means the function that maps each world to n. So roughly, what we want is that the usual natural numbers are embedded into our framework by this operation, using this operation, right? So for each natural number, you have the corresponding constant function that behaves in the very same way at each world. And the standard interpretation of the predicate being specific is, of course, like that. So it's BBF, right? Blackboard bold F. So it is just the collection of all these constant functions. So which arbitrary numbers are in fact specific? Well, those that are constant functions, right? So if you have a constant function, it corresponds to some n, and this is a specific natural number. So this is the standard interpretation we have in mind. Nevertheless, for some time, right, for like 5 slides or so, I will also allow SP to be also interpreted by other subsets of this beautiful W. So I will also allow for other interpretations of the predicate being specific, And then we will see that, in fact, there is a very simple formula, or rather a sentence, that fixes the interpretation of SP so that we can always deal with the standard interpretation if we want to. So in fact, it is expressible. But I'm going to say more about that in like 6 slides or so. And then, as usual, you define the semantics. So suppose that now we interpret the predicate of being specific by some subset of the individual concepts, right? So elements in this capital F are treated as specific natural numbers. Of course, I mean, if F equals BBF, this is the standard interpretation. But in general, I mean, for the time being, I will allow it to be interpreted by other subsets as well. And now we define what it means for a formula phi to be true in this structure at a given world W under a given valuation, right? So let us go through that carefully, right? So this is just a set of worlds. We're working within S5, so we don't need the accessibility relation. So we have a set of worlds, and we have some interpretation of the predicate of being specific. So this is roughly our model. I will call it a structure, right? A structure over W. And we have some element of this capital W, a given world. And since phi may contain 3 variables, we also need to fix some interpretation for these variables, which is a valuation, gamma, that maps all the variables, or rather all the 3 variables, to some individual concepts, right? And now we want to define what it means for this formula to be true in this structure at a given world under a given valuation, written like that. So here is the subscript. Small w says that at which world you are, and at some point we would like to omit this world, because intuitively worlds do not matter, right? So all the worlds, they should be like interchangeable. It doesn't really matter at which world you are. When you're talking about arbitrary natural numbers, it's like you're imagining all the possible worlds at the same time. So we're going to formalize that in a minute. So suppose that for the moment we have like 2 terms, T1 equals T2. What it means that this formula is true. So this is very simple. There is some function that corresponds to T1, and there is a function that corresponds to T2. And we just want to make sure that they coincide at a given world. Again, equality is a coincidence at a given world. If you want to have like the global equality, you just take the box, right? And it will be clear from the interpretation of box that it will work nicely. So negation is negation, disjunction is disjunction, conjunction is conjunction, if you want to include it as a primitive. Exists means exist, like in first order logic. So exists x phi is true on the gamma if phi is true on the evaluation. That is exactly like gamma, except that it maps x to some individual concept, right? If you want for all, you will say for all. Diamond means it is possible that that phi is true at some world. Since we have the universal accessibility relation, I don't say that this world has to be accessible from W. All worlds are accessible from each other. Somehow it will still, I mean, affect the expressiveness of the language, but formally we don't have the accessibility relation at all. Well, of course, box means for all. Well, box may be treated as an abbreviation for not, diamond, not, right? And specific means that the corresponding function, I mean, gamma of t, belongs to f. So this is why we have fixed some f. Here it is just a set of individual concepts, and in the standard interpretation, so to say, it will be BBF, the collection of all the constant individual concepts, the collection of all constant functions from worlds to natural numbers. Okay. Now, and since we want actually to get rid of this W, because somehow all the worlds are interchangeable, in general. I'm going to introduce one more definition. Namely, I will say that phi is true in this structure under gamma without mentioning the world, if it is true for all worlds. So whatever the world is, it has to be true. So in this notation, let me draw something. So in this notation, implicitly, I assume that we quantify over all the worlds, right? Okay. Now, in the case when F has its standard interpretation, when specific has the standard interpretation as the collection of all constant functions, I will use this notation instead of that one. And similarly for this notation. So I will simply drop F because F has the standard meaning, right? It's just the collection of all standard functions from W to natural numbers, to the natural numbers. It is easy to see that the set of all purely arithmetical sentences where there are no modal operators and no occurrences of the predicate of being specific. So if you take the collection of all purely arithmetical sentences true in a given structure, it will simply coincide with the first order theory of the standard model of piano arithmetic. So it's very easy, right? Because there is no need to go to other worlds. And at each world, I mean, the semantics is standard, right? So for every else, also for every else sentence, right, in the general language, we have the following: that if F has its standard interpretation, this is important, that if it is interpreted as a collection of constant functions, then a sentence, a formula without free variables, is true in all worlds if and only if it is true in some world. Note that previously we said that for all worlds, and here we say for some world. So somehow, as far as sentences are concerned, and as far as the interpretation of being specific is standard, there is no real difference between for all and exists, right? Here. So you may easily pick one of the worlds. They are all indistinguishable from each other. And if something is true at one of these worlds, then it's true in all the worlds, and then you're good. I mean, the formula is true. So for some and for all mean pretty much the same, in this, provided that the interpretation of the predicate being specific is standard, and you have no free variables. Further, I mean, it's very easy to see that the compactness will fail already for purely arithmetical formulas, but there is no surprise here because, I mean, we assume the standard model of piano arithmetic on the background. And of course, the compactness will fail. So otherwise, we'll easily get a non-standard model. So this is not a big surprise. But there are some surprises coming. And but before going to that, let me give a few more simple. Let me make a few more simple observations about this. So first of all, about the Barkhan scheme. Well, the Barkhan scheme, it consists of all the formulas of this form. In standard model logic, it corresponds to the constant domain condition. But in standard model logic, you quantify over elements of a given domain, not over individual concepts. Still, I mean, this formula, it will be okay. And this formula and its converse, they will be true in all the structures, whatever the interpretation of the predicate being specific is. So it doesn't need to be standard. So it's very easy that this formula will hold, simply because in all the worlds we have the standard model. So you only need to take a closer look at the predicate of being specific, that it will not ruin anything. On the other hand, what is interesting is that in all these structures, the so-called Gilardi scheme, which is actually, I mean, it's pretty much like the converse of the Barkan formula, with for all replaced by exists, right? It can be regarded as a choice principle. And this formula will fail already for the SP-free formulas, while its converse holds. So not for purely arithmetical formulas, we still need the model operator, but we don't need the predicate of being specific. And this formula will fail. So let us take a closer look at why it fails. So it says that if it is necessary that, so if at each world there exists some x such that phi holds, then there exists some 1x such that box phi, right? But here exists x means there exists an individual concept, right? So let's take a closer look at that. Consider this formula, psi. So what it says is that our x, which is an individual concept, it either coincides with zero, not like it's identical to zero. It's like at a given world, it's either coincides with zero, or it is impossible for x to coincide with zero, right? So it's either zero or it's impossible for it to coincide with zero. So like in no world it is zero. Then one easily checks that the premise of the Gilardi scheme, where phi is replaced by psi, will be true, and the conclusion will be false. So let's take a closer look at that. So this formula says that it is necessary, like in each world, to find an individual concept that satisfies this formula. Of course, this is true, right? Because you can take the zero individual concept, right? And it will satisfy this formula. Still, it is impossible to find one individual concept that will necessarily satisfy this formula, because otherwise, like, it has to be necessary, it has to be zero, and at the same time, it cannot be like zero necessarily. Okay. Now, given all that background, let us shortly revisit the example from Kit Fine's paper. Let us briefly reconsider that example that concerns odd and even natural numbers, right? So denote this formula as even and this formula as odd. So even says that our x can be represented as y plus y for some individual concept y. And here equality means just a coincidence. And odd means that, okay, it's y plus 1. Now, and pick an arbitrary natural number such that its set of values, its range, contains both even and odd specific natural numbers, right? So that it is not it's not always even and it's not always odd, right? So it's somewhat rather arbitrary, right? Then evidently, it is not even at all worlds, and it is not odd at all worlds, and this is okay. But at the same time, it is true that for all x, it is even or odd, because whatever the world is, pick an arbitrary concept, it will be at each world either even or odd, because equality means coincidence. And since this is true for all the individual concepts, it will be true for our individual concept alpha. So since implicitly we have quantification over possible worlds here, you may have this situation that alpha is not even in general. It is not odd, like if you go through all the worlds, and yet alpha is even or odd, right? So there are two catches here, of course, is that equality is actually treated as a coincidence at a given world, not like the global equality. And the second catch, of course, is that somewhere here you have quantification over possible worlds, which is implicit. And now it seems that your example is pretty much okay within this formalism. Now I'm going to say a little bit more about the mathematical properties of this framework, how expressive this framework is, what can be defined in this framework, so that you get a better feeling of what this framework is about and how complex it is, what questions may be asked about it. Now, first I'm going to say something about definability. Suppose that you have suppose that you have a relation on arbitrary natural numbers, or a relation on individual concepts, not a relation on natural numbers, right? Keep that in mind. We're going to discuss relations on the natural numbers later on. But for the moment, just a relation on individual concepts. We say that this relation is definable in the structure, just like in first order logic, essentially. If there exists a formula, phi, such that for every tuple of individual concepts, this tuple belongs to R if and only if the corresponding formula is true. Note that here we have, again, an implicit quantification over possible worlds. So this is important to keep that in mind. If the same formula, phi, defines this relation R in all the structures over W, so so we consider different interpretations of the predicate of being specific, and whatever the interpretation of the predicate being specific is, the same formula defines R in the corresponding structure. So if this is the case, if it happens to be the case, then we say that R is uniformly definable. So uniformly definable means that whatever the interpretation of specific is, right? And as usual, one can speak of definability of arbitrary numbers, I mean, like concrete numbers or functions on them, because a concrete concept may be identified with its singleton, and a function may be identified with its graph in the usual manner. So I'm going to focus on relations. Again, like in first order logic. Now, for instance, the identity relation on the individual concepts is uniformly definable by this simple formula. We already saw that. So here is the formula, right? And therefore, the coordinate-wise addition and multiplication can be uniformly defined by these formulas. This one and that one. So this thing is not coincidence. It's not the usual equality. It's the global equality. So this is that thing. Oh, sorry. And here it is the same. Now, clearly, as far as definability is concerned, there is no significant difference between the signature of piano arithmetic and, say, this signature, the smallest signature, and in effect, any other signature will do as well, provided that the standard model of that signature and the standard model of piano arithmetic are first order interdefinable. So it's not important that you have addition and multiplication, or addition and multiplication and the successor function, or maybe something even trickier, like the successor function and the divisibility relation. There is a famous result by Julia Robinson that you can define addition and multiplication in that structure. So it's just, you just want it to be like first order interdefinable with the standard model. Now about specific natural numbers. So far we have assumed that the interpretation of specific of SP may vary, but in fact it is very easy to fix that interpretation, and it's surprisingly easy to do that. So let us do that. I mean, in like 3 lines. Now, henceforth, by specific numbers, I will mean elements of these BBF, right? That is constant functions. Of course, I mean, the definition of what is a constant function depends on the choice of W, set of worlds, but still, I mean, constant functions over W. So these are like standard specific numbers for a given set of worlds. And now you can easily define these formulas. A0, A1, and so on. So A0 says that X is necessarily 0. A1 says that it is necessarily the successor of 0, and so on and so forth. And it's very easy to see that these formulas will define, the formula AN will define the specific number N uniformly, right? Whatever the interpretation of specific is, because we don't use the predicate of being specific here anywhere. Well, this is not surprising at all. This is just a very trivial remark. But furthermore, I mean, a slightly more interesting remark is that it is not hard to obtain the following proposition. That for any alpha, for any individual concept, the following are equivalent. That alpha is specific, it is uniformly definable in W, or it is definable in the standard interpretation, in the standard structure over W. So let's think about it for a moment. So specific means that, well, it has a very specific concrete interpretation. It's just a constant function. Uniformly definable means it is definable by one and the same formula in all the structures over W. And here it says that it is definable under the standard interpretation. So in the standard structure over W. So it turns out that all these are the same, and in fact, they can be used interchangeably. So uniformly definable is not a very interesting notion from that perspective. It just coincides with the notion of being specific. Curiously, you can further fix the intended interpretation of the predicate being specific by means of a single sentence, right? So, and this is how you do that. So you just take the conjunction of all these sentences. So let us go through these sentences. So first of all, you say that if something is necessarily 0, then it is specific. Of course, the 0 function has to be specific. So you want to have that, and this is what the first formula says. The second formula says that if something is specific, say the 0 function, then the corresponding successor, the corresponding function plus 1, right? So if you take that function and that plus 1 for each world, then the resulting function will still be specific, right? So the constant function 1, the constant function 2, they will all be specific by B1 and B2. But this is not all, of course. You want to say that there are no other specific concepts. And you can also easily do that. You simply say that if something is specific and it is not 0, then there is a predecessor of that. So again, this thing means necessarily, right? So, and roughly, if you have like the constant function 1, then its predecessor will be the constant function 0, and so on and so forth. So everything is good there. But if you have a function that is not constant, then you take just the minimum of its values. Say it's 5, right? And in 5 steps, you will reach 0, right, in one of the coordinates, but then you will not be able to take the predecessor function. So it's very easy to show that this B3 guarantees that there are no other specific individual concepts except for the constant ones, right? And one readily checks that the conjunction of these does the job. So this is what I've already said. For any interpretation of SP, if the conjunction of these simple sentences holds, then this interpretation F has to be the standard interpretation. It has to be BBF. And of course, if it is BBF, then the conjunction holds. And given that, since you can easily fix the standard interpretation, for the rest of the talk, I will focus on the case when F has its standard interpretation. So it's SP simply means the constant function, a constant function. Okay. Right. Now, since we have already fixed the interpretation of SP, right? And we know what are the natural numbers. We're working over the standard model of Peano arithmetic. And the accessibility relation is just the Cartesian square, just the universal accessibility relation. The question is, what matters, right? And perhaps the cardinality of the set of worlds matters. Of course, it is not important what worlds are, right? I mean, but it may be important how many worlds we have, right? There is no accessibility relation on them, or the universal accessibility relation if you want. But I mean, the size of the set of worlds may matter, right? So it makes sense to consider different sets of worlds, I mean, different cardinalities, and to see whether the corresponding theories will be different. So for that purpose, let me introduce the notion of the theory, of the L theory of W. So by the theory of W, well, I might have said that by the theory of some structure, but since, I mean, F will have the standard meaning always, the only thing we need is W, right? The set of worlds. By the theory of W, or the theory of the standard structure over W, we understand the set of all sentences that are true in W, right? Or rather in the corresponding structure for all the worlds again, right? So more explicitly, it can be written as follows. So you may like explicitly say that you're working over the standard model of Peano arithmetic because you can try to do the same over the natural numbers. I mean, the standard structure of the natural of the real numbers, sorry, and over some other standard structures. So in fact, I mean, this structure may vary, but we want to talk about natural numbers for the moment. Now, notice that each cardinal A can itself be viewed as a set of worlds of cardinality A. So A is just some very concrete set of the same cardinality, right? And there is a proposition. It's not difficult to show that there exists a sentence phi such that for every cardinal A, if phi is true in A, if it is true in the set of worlds of cardinality A, that is, then A equals Aleph 0. So you can somehow fix, you're able to say by means of a single sentence in this language, over the standard model, of course, that the set of worlds is infinitely countable, right? So, well, of course, that means that the Leeuwenheim's column theorem will fail, I mean, upwards and a lot of other things. So somehow you're able to fix that. And what it means in particular, that if you take the theory of Aleph 0 of some set of worlds of cardinality Aleph 0, then it will be different from the theory of any other cardinal. So if you have exactly Aleph 0 worlds, and if you have a different number of worlds, I mean, the corresponding theories, they will be different. So it is possible to distinguish these theories by means of this sentence. Well, since the language we're working with, this Carnapian language, allows us, well, at least over the standard model, to distinguish Aleph 0 from the other cardinals, the reader may well ask whether we can do the same for Aleph 1, Aleph 2, Aleph 3, and so on, and whether that depends on the continuum hypothesis or something like that. And the question, the answer to this question turns out to be negative, as the next result shows. So let us take a closer look at that. That for any cardinals, A and B, if the minimum of A and Aleph 1 equals to the minimum of B and Aleph 1, then their theories coincides. So roughly what it means is that you're able to distinguish all the finite cardinals from each other by means of this language somehow, probably, right? You're probably able to distinguish Aleph 0 from Aleph 1, but everything above Aleph 1 has the same meaning as Aleph 1, right? So for instance, the theory of Aleph 1 will correspond to the theory of Aleph 2, Aleph 3, and so on. And it makes no substantial difference whether we have a continuum of worlds 2 to the degree Aleph 0 or Aleph 1 worlds. And of course, no assumption about the continuum hypothesis have been used to prove this. The language is able to distinguish countable from uncountable, but everything that is uncountable is treated the same. Yeah, as for finite, as for concrete natural numbers, the condition that our set of worlds has cardinality n can be expressed in the language. So, I mean, it's easy to write a formula that says that the set of worlds has cardinality n for each n. It's not difficult to do that. Well, and finally, a few words about how the general framework, how complex it is. Well, the brief answer is that it has the same expressiveness as second-order arithmetic, right? So let us go like briefly through that. So I'll say that a relation on natural numbers, on standard natural numbers, is absolutely definable in W if there is a formula such that a tuple of natural numbers belongs to P if and only if the corresponding tuple of constant functions satisfies phi in W, again, like uniformly through all the worlds. And it turns out that if I'm given a second-order formula with natural number parameters, then you can recursively, like computably, find a formula in the Carnapian logic such that it defines the same set. Well, up to this mapping, right? Such that a tuple satisfies the second-order formula if and only if the corresponding tuple of constant functions satisfies the translation. So, and if the tuple is empty, then this tuple is empty. So you have a reduction. You have a reduction of complete second-order arithmetic to the theory of the natural numbers in the Carnapian framework. Whatever the set of worlds is, provided that this set of worlds is finite. So this is an important observation, right? So provided that it is finite, you can, infinite, sorry. Provided that it is infinite, you're able to reduce complete second-order arithmetic to this language. And in fact, I mean, wow, this part is rather straightforward. So if you take a look at the proof, I mean, it's like, I don't know, half a page or something. But surprisingly, it turns out to be significantly more difficult to prove the converse, that we cannot get more than second-order arithmetic. So there is a function, a computable function, that maps formulas in the Carnapian framework to formulas in the language of second-order arithmetic, such that, well, similar equivalence holds, right? So in particular, it means that these theories, so for every infinite set of worlds W, the corresponding theory will turn out to be like computably isomorphic. It will have the same complexity as complete second-order arithmetic or elementary analysis. And the second part is somewhat more difficult to show. Well, and also it will mean that for every infinite set of worlds W, the set's absolutely definable in W. Well, absolutely means like that under this mapping that maps each natural number to the corresponding constant function. That the sets absolutely definable in W are precisely the analytical sets. I mean, the sets definable in second-order arithmetic. For finite sets of worlds, this is not so interesting. You get like arithmetical sets in first-order arithmetic, and the theory will be completely isomorphic to complete first-order arithmetic. But there is no surprise, because I mean, the set of worlds is just finite, and you can model that within first-order arithmetic easily. For infinite set of worlds, provided that you don't know how many of them are, it's slightly more difficult. Well, and this is pretty much it. Let me say just a few words about the references. I haven't mentioned them so far. So the main reference is our joint paper with Leon, published in Journal of Philosophical Logic in 2019. The inspiration for that approach comes from this small note by Saul Kripke, who also mentions Kit Fine. So here's Kit Fine. His approach is drastically different, but some motivation comes of it. And also Leon Horsten has published a whole book on the metaphysics of arbitrary objects. Well, mainly about metaphysics, I will say, not so much about mathematics. There are not so many mathematical details here, but still. In Cambridge University Press. And recently also Leon has published a philosophical paper on using Boolean valued models for modeling arbitrary objects. And there are still quite a number of details missing there. So, I mean, the logical part, I believe, is not like, it's still in process. But this is a different approach, and we discussed it back in 2018, I believe, and there are still a lot of interesting open questions related to both this framework and the other framework, I mean, the Boolean valued framework, that is not even developed in detail at the moment. So there is something interesting going on there, and I have some open problems on the back of my head as well. That's pretty much it. Thank you very much for your attention.